I want to thank the organizers for putting out such a nice program, and thanks everyone for coming to the talk. So today I'll talk about feature learning in two-layer neural networks, and in particular, I'm going to focus on how the input covariance structure enters the picture when we talk about learning target functions. So throughout the talk, we're going to focus on a student-teacher setting, which means that there is a statistical model that generates the data. So we are in the regression supervised learning setup. We have the input d-dimensional x. We have an unknown target function f star. Whenever there's a star, it's an unknown function. We add a bit of noise, and then we get the response variable. This is how the data is generated. And then getting n samples from this model, and we write down the empirical risk and minimize this entity over a class of functions f. So it could be like linear models, it could be neural networks, and so on. I'll be more specific about this, but we get n data points, and then we minimize the empirical risk, and that is our estimator for this function f star that is unknown. Okay, so we need to measure its accuracy of this approximation that we're making, and that's going to be through the prediction risk. So we have this expected squared error loss between the function we just obtained through minimizing the empirical risk and difference to the true ground truth function, unknown function f star. And you look at how small this is, smaller is better. So we're going to hope that this goes to 0. So we say f actually learns f star. Okay, so majority of the talk, I will focus on the proportional regime, which means that n and d are comparable. So one of them is not polynomial in the other one. So they go to infinity. They're both very large, and their ratio goes to some constant psi, which is an important parameter. So we're going to keep using this. So it's good to memorize it. It's the larger psi means that the sample size is larger compared to the input dimension. So this parameter will come up. Now, why is this interesting? Well, I can claim that it's a realistic setting. In practice, we have number of samples comparable to the dimension. But I think from a theory point of view, it allows us to get precise characterization of the risk. So you can actually compute this performance metric exactly in this limit. So that's why it's quite interesting to focus.
Can you just say a word about why it's interesting to look at the limit as n and d go to infinity rather than at a fixed finite value?
Yeah, so instead of getting upper bounds, we're going to get, well, there will be some upper bounds too later. But in some cases, you can actually get this risk, calculate this risk exactly. And that's through this limit. But in some cases, we need to resort to upper bounds, and I'll tell you when it shows up. Okay, so the targets that we are going to consider is single index models. So this is a class of targets that come up in statistics quite often. What it means is that the target function depends on the input x through this unit vector beta star. And there is a nonlinearity on top. So the star things are unknown. Here, beta star is a unit vector we don't know, and sigma star is a nonlinearity we don't know. We want to learn both of them using neural networks. And the input is Gaussian with some covariance. And now I'm going to show you how this covariance actually, like the type of covariance matrices that we're going to consider. The first one is the isotropic covariance, where now the blue contours are the distribution of the x, that's the input, and beta star is this unknown target direction. You see that input is not informative about the target. So this is kind of like harder case. The second type of covariance, we're going to consider a spike covariance matrix, where sigma is identity plus some theta, spike magnitude theta, and direction mu. So what does this mean? Mu is the direction of highest variance in the input, right? So if you look at the contours now, mu is the direction of highest variance. And now I'm assuming that it perfectly aligns with the unknown target. Now, input data has a lot of information about the target. This is quite idealized setting. You wouldn't expect this to happen in practice. in the last setting, we're going to relax this. There is the direction of highest variance, and there is the true target direction. There is some positive angle between them, but it's not perfect. And we're going to see, overall, the goal is as follows. So we have the spike magnitude theta, and we have the alignment, the angle between this mu and beta star. How do they interact with each other? How do they actually affect the learnability of the problem we have? This is kind of, now I'm gonna, in 3 sections, I'm gonna do each of them, and then let's start with the isotropic covariance. So the important student model, the model that we train, is a 2-layer neural network. So this is what you're seeing on the right-hand side of the graph. The input is d-dimensional. You multiply with the first layer weights, and then apply nonlinearity. And there are n, uppercase N hidden units here. And then multiply with the second layer weights, get the output. So this is in matrix vector notation written in this display equation. And the number of neurons here also go to infinity, and ratio to the dimension goes to a constant, just like in the proportional regime. But this parameter is not very important, so you don't have to memorize. N over the small case, N over the psi here, that's an important parameter that'll come. But the width also is going to infinity, and everything is proportional. Now, the training here means that you optimize over the weights, you optimize over the first layer weights, you optimize over the second layer weights. But the key point is that we want to talk about effective feature learning, representation learning. What that means is basically the output of this first layer is serving as a feature map for this whole problem, right? And then you're doing kernel ridge regression on top, basically, if you do L2 regularization. No, so what is important here, you're training the first layer weights, and that's actually training the feature. So can we demonstrate the effect of learning the features on this learning problem? And that is through the optimizing the first layer weights. And that is a gradient descent on the first layer weight. So this is the training procedure that we're going to stick to for the 2-layer neural network. So we do 1-step gradient descent on the first layer. So this is that. Only 1 step is sufficient. You can do more steps as long as the number of iterations is constant. Okay, but for simplicity, we're going to just take 1 gradient descent iteration, and this is going to be the trained first layer weights. Now we take this and then plug it into the feature map, basically the output of the first layer, and then run ridge regression on top. Now we trained the second layer entirely. We did 1 gradient step on the first layer, and then these together will give me a prediction function, which I call neural network function. And then I'm going to calculate its prediction risk and call this risk of neural network. Okay, so this is the training procedure, and we want to show that this actually is smaller than some baseline, right? We want to show this neural network, the risk of neural network is small compared to some baseline, and that baseline is going to be risk of some kernel methods. So student model 2 is pretty much our baseline and what we're going to compare neural networks against. So the first one is the random features regression. So what is this? Why is this interesting? Because if we can characterize this behavior of the random feature regression, we can compare neural networks to, again, neural networks, but there is no feature learning. So if you don't train the first layer weights, keep it at initialization, train only the second layer. Now we did not train the feature map, then that is actually random features model. So this is one kernel method that we're going to compare neural networks against. And the second one is the kernel ridge regression. Just fix a kernel, inner product kernel, rotationally invariant kernel, and so on, and look at its performance. And their performances are actually very well understood. There are precise risk curves. So these are like precisely calculating this prediction risk and showing, you can see the double descent phenomena and so on and so forth. But the important thing is none of these have feature map learned. So there's no representation learning happening here. So the goal is to demonstrate the representation learning. Now, this slide may be a little bit complicated, but the takeaway message is as follows. So I'll first tell you what it is and then do it in math. So this is saying that kernel methods can only learn linear functions in the proportional regime when the input is isotropic. Kernel methods can only learn linear functions. So now I'm going to do that in a slightly more complicated way. You take this target function f star, you write it as the linear component plus the nonlinear remainder. So basically, you project this nonlinear function f star onto a set of linear functions in L2. And this nonlinear component is going to be, well, L2 norm of that actually is going to be lower bounding the prediction risk of the kernel methods that I've shown you in the previous slide. So what does this mean? Risk of these kernel methods can be only as small as this norm, L2 norm square of the nonlinear remainder part. Now, why is this interesting? Well, we want to learn. That means we want these risks to go to zero. So that means that it cannot go to zero unless this guy is zero. And if this guy is the nonlinear remainder is zero, that means that we're only learning linear functions. Now, this is a convoluted way of introducing this, but the reason is as follows. In the figures that I'm going to show you, there will be a dashed line. And in all of them, that will mean this kernel lower bound. And the goal is that kernels need to abide by this lower bound. And we'll see if neural networks can break it. That's kind of one motivation. Again, the dashed line is the kernel lower bound, and this is true in the proportional regime when the input is isotropic. Okay, so I'll give you the first result on neural networks. So this is when in the isotropic setting, learning rate is small. So we make a non-degeneracy assumption where the expected value of sigma star prime is non-zero. So this non-degeneracy assumption, for now, let's just state it as is, but I'll come back to it, and it's actually related to a concept of information exponent. Second assumption is Gaussian initialization. This is kind of standard, I guess, also in practice, but in a lot of the papers. So here is the first result on when this learning rate is small. The colored names are the student authors, the Jijao and Denny is kind of leading authors in this paper. So what it says is that it compares the risk of the random features model, or the kernel methods actually, to the risk of the neural network. So let's call this difference delta. So larger the delta means that we are doing better, and neural networks are doing better. So this can be exactly characterized. So you can actually calculate it precisely, write an exact equation, which is very ugly. So that's why I'm not showing it to you. But you can actually show that it's a non-negative function. So that means that if you train the first layer weights, you train the feature map, you're always doing better than random feature model, the untrained version. And another interesting thing is it's an increasing function with respect to the learning rate. So larger the learning rate, better your feature map is. Now the figure looks like this. This is okay, so the x-axis is the important parameter psi. So to the right, you have larger sample size. Y-axis is the prediction risk. And brighter the curve here, larger the learning rate. But what you should notice is that the kernel lower bound is here. Neural network cannot actually beat this kernel lower bound. And that is because we are focusing on the small learning rate regime. It's always doing better, but it cannot beat the kernel lower bound. That means that there will be okay. I think that's a good enough statement to kind of depart from this slide. The goal was to beat this lower bound. That means that we actually need to take a larger step size and kind of leave this linear regime. And the large step size is for the square root of the width. So what is good about this is this large step size allows you to leave the linear regime. So that means that you'll learn nonlinearities. The bad thing about it is now we cannot do precise risk calculations. So there is no precise asymptotics anymore. Now we have to resort to the upper bounds. And the second result in this domain, when the step size is large, is as follows. What it really says is that the risk of the neural network is upper bounded by some constant tau star, plus something that decays with the sample size, but I can increase the sample size and make this go to 0. And if this tau star is smaller than the kernel lower bound that I would like to beat, then I'm pretty much done. Now it has to be specific to some target activation pairs. This tau star can be calculated. And for these target activation pairs, you can actually compute tau star and it's smaller than this kernel lower bound. But in particular case, this when they're both error function, then this tau star is 0. So the risk is O for their psi inverse. So remember, psi was small when, psi was large when sample size is large compared to the dimension. So you're basically getting this linear behavior. So what is this plot? X-axis is the sample size, y-axis is the prediction risk. As you increase, so this is when this, so brighter color is the larger step size. This is when the step size is 0.1. So you're not able to beat the kernel lower bound, but as you increase the learning rate, you're actually able to beat the kernel lower bound. That means you're learning non-linearities. Okay, so yeah.
But this is under a specific data generative model.
Yes, exactly. This is the statistical model that's basically the single index model that I have this error function as the nonlinearity and it unknown direction. Correct.
And it's a Gaussian.
Input is Gaussian, isotropic Gaussian so far. Now I'm done with the isotropic Gaussian. I'm going to introduce data covariance and look at this effect. Looking at this plot, this actually shows me that the error is going, the prediction risk is going to 0 with a rate of 1 over psi. So this kind of suggests a learnability definition. Now, here's the learnability definition that I would like to use. Basically, if I increase this parameter psi, can I make the risk arbitrarily small? That's my learnability definition. Larger sample size, can I make this risk small?
In what sense is it different than the fact definition? Because the fact definition tells me for every epsilon and every d, I have n that will suffice.
So with
there's no for all distributions.
Plus there is not,
I don't know
it's with probability 1, right? The risk is going to be small with probability 1.
And
Yeah, so here it's with probability 1.
but it's in the limit.
Yeah, in the limit, exactly. Yeah.
I see. So rather than convergence in probability,
Yeah,
this is convergence in arbitrary.
well, this is conversion with probability 1. Okay, so now I'm going to consider this in different covariance structure, which basically there's the direction of highest variance aligns perfectly with the target direction beta star. So I have this input coming from this distribution, Gaussian with the spike model. And then there's a teacher model, which now has this extra scaling, but you can ignore it. It's just to have a unit norm. And sigma star is going to be a degree P polynomial. So it's kind of like adding complexity to the problem. Now, why is this degree polynomial is an important thing to keep an eye on? Because remember the kernel lower bound in the proportional regime, when the input was isotropic, we could only learn linear functions. That means P has to be 1 if the input is isotropic. But if now input has this covariance structure, then how large should theta be so that kernel methods can learn a degree P polynomial? So this is one question we could ask. And same as this, we can ask the same one for the neural networks. But for the neural networks, we have to look at the non-degeneracy assumption to ask a similar question. Now, this non-degeneracy condition, expectation under Gaussian measured first derivative of sigma star, is non-zero. So where is this coming from? You can write down the Hermite expansion of this target function. And this condition is equivalent to saying that the first Hermite coefficient is non-zero. Okay, so this is, again, a convoluted way of defining this condition. But this is in very much related to this notion of information exponent, which was introduced in one of Akosh's earlier papers. It basically says the K, the information exponent K, is the smallest such alpha K, which is non-zero. The smallest non-zero Hermite coefficient, that is K. That is the information exponent. So this is another complexity measure that neural networks actually pick up. But if this notion was like, you haven't seen it before, this example is enough to keep in mind and carry on for the rest of the talk. Now, consider this polynomial, which is a degree 5 polynomial. And the smallest degree monomial is 1. Largest degree monomial is 5. Polynomial degree of this polynomial is 5. And the information exponent is 1. Good thing about this is polynomial degree is always greater than equal to the information exponent. So, but this example is enough to keep in mind. So P is always larger than K, greater than equal to K. So what are the prior results say? We have the kernel, for the kernel methods, kernel ridge regression, the sample complexity to learn a degree P polynomial, to learn this polynomial, the sample complexity has to be of order D to P. And for the neural networks, the sample complexity has to be of order D to K. Now, one of them is kind of picking up the polynomial degree. The other one is the information exponent. But remember, we wanted to stick with the proportional regime. That means that N and D are comparable. One of them is not polynomial in the other one. So that means that we can learn with the kernel methods only degree 1 polynomials. With neural networks, neural networks can only learn functions with information exponent 1. Now we want to learn more complex functions, higher degree polynomials, higher degree information exponent. And for those, we actually need to introduce anisotropy. So spike theta is going to help. We have the spike magnitude theta and direction beta star. And we also have this target function f star. We assume sigma star is a degree P polynomial with information exponent K. And P is always greater than K, so that's going to be important. The first result is sort of a negative result on the kernel ridge regression. It's kind of like mimicking the lower bound that we had, the kernel lower bound. So kernel ridge regression cannot learn this target in the proportional regime unless the spike magnitude is this much. Smaller than this order, kernel ridge regression will fail and not going to learn. So kind of a negative result. And the positive result on neural networks is a ReLU neural network is able to learn this target if the spike magnitude is of order this much. Now, we can argue that if P is always greater than equal to K, there is a separation between them, but the following figure is kind of making this comparison easier. Since the information exponent is always smaller than equal to P, the polynomial degree, we have the following plot. So x-axis is the dimensionality, and the y-axis is the signal magnitude theta. So what these two results say, one of them is negative, the other one is a positive result, right? What these two results together say is there is a regime where neural networks and kernel ridge regression both succeed. There's a regime where kernel ridge regression actually provably fails, but neural networks actually succeed. And there's a regime that they both fail. So there's a clear separation, provable separation between two-layer neural networks and the kernel ridge regression in this case. So how much time do you have? Okay, great. Okay, so this is kind of this was the idealized setting when the spike direction perfectly aligns with the direction of highest variation. Now we're going to relax that assumption. We're no longer in the proportional regime from this point onwards. We assume that the data is coming from a spike model where the direction of highest variance is mu. And this is this guy here. And then we have the teacher model where the target direction is beta star, and the teacher model has this information exponent k. Now, why is this interesting? Actually, this is exactly the reason. If you open up like any applied statistics book, there is a pre-processing on the data, and basically to reduce the dimension, you would get the input, run PCA, and regress on the low dimensional covariates. This is exactly kind of mimicking that in a simplified setting. So that's kind of the argument that this model makes sense. And now we're going to look at two parameters and how they interact with each other and also interact with the sample complexity that is needed. The first one is the spike magnitude, theta, and the second one is the angle between mu and beta star, direction of highest variance and the target direction. Okay, so the non-degeneracy condition in this case, since the setting is a bit relaxed, it gets a bit complicated. So here is the statement, and I'm not going to focus on this, but what this really says is it's a not very transparent condition that you need to verify for specific targets and activation functions. For example, if you're interested in phase retrieval problem, which is information exponent 2, you can take the activation function ReLU, or you can also consider if the model is specified, means that the link function is known, this condition is satisfied. So it needs to be verified in a case-by-case basis. Okay, so given this new non-degeneracy assumption, I'm going to introduce two parameters now, gamma 1 and gamma 2. The alignment between the spike and the input direction is going to be d to the minus gamma 1. So larger gamma 1 means less alignment, smaller gamma 1 means more alignment, and spike magnitude is d to the power gamma 2. Now, given this parameter gamma 1 and gamma 2, the sample complexity that you need for a two-layer neural network to learn a target with information k, exponent k is given by this expression. So in this result, the student author is Alireza, who's also over there. If you're interested in this result, talk to them. We also had a poster. So there are three regimes of sample complexity, and they're actually defined by the interaction between these parameters, gamma 1 and gamma 2. So depending on how they interact with each other, you get these different sample complexity regimes. Now, instead of looking at this figure and trying to make sense of it, we can look at the following plot. Now, on the x-axis, we have this spike target alignment. Here, gamma 1 small, meaning this is more aligned regime, and this is less aligned regime. And on the y-axis, we have the spike magnitude. So I'm going to look at a few edge cases and conclude. If the gamma 1 is 0, so that means the perfect alignment case, we are in this vertical slice. It puts us in the easy regime. We always get the kind of the best sample complexity we can achieve. If gamma 1 is 0.5, so this is an interesting case where the spike direction and the target direction can be entirely independent, two independent random vectors sampled uniformly on a unit sphere. Then you're in the hard regime, but if the spike magnitude is large, even if they're entirely independent, you can get to the intermediate regime, so which I find it interesting. And then at any point you slice this figure vertically, you start from the hard regime for small spike magnitude, and if you increase the spike magnitude, it gets you to the intermediate regime and then the easy regime, which kind of makes sense because the problem dimension is getting smaller and smaller. Okay, so with that, I'll summarize and conclude. So I talked about three different data covariance setting, the uninformative input, that is the isotropic data, talked about small learning rate and large learning rate, was able to learn nonlinear functions. And we talked about the perfectly aligned, idealized case where and showed that neural networks adapt to this additional low dimensional structure more efficiently compared to the kernel methods. And lastly, we looked at the misaligned setting where it's not the idealized setting now, but and we also are not in the proportional regime anymore, but we can actually define 3 different regimes of sample complexity depending on how the alignment and the spike magnitude interact with each other. So with that, I'll leave this to open questions here and conclude. Thank you so much.